working with Ari Leor, who's an expert on, particularly on AGN. So most of his work has been on AGN and looking at AGN and their hosts. And so today he's going to tell us about that work.
Okay, so thanks for coming to the talk. So there's, I think, mounting evidence that the active galactic nuclei, the black hole at the center of the host galaxies, affects structure formation.
Sorry, you might want to put your microphone on.
Ah, okay. Where's that?
This
Sorry.
is for recording purposes only.
Is that?
Yeah.
You did this?
Well, no, I had to see when the table sometimes to work because sometimes it's really loud. It's on.
Okay. Oh.
It picks up, yeah. I already turned it on.
Sorry.
Oh, no, it's fine. Just sometimes the bar just goes like.
I know.
Okay.
Yeah.
So there's mounting evidence that the active galactic nuclei, they affect the structure formation or the star formation in their host galaxies. And my thesis focuses on comparing, well, finding more observational finding more relations between these active galactic nuclei and their hosts. And we do this just by comparing the properties of the active galactic nuclei and the properties of the host. Okay, so I want to start by a general introduction to active galactic nuclei, and then I'll present the more specific questions that I want to answer, and then I'll try to answer them. Okay, okay, so I want to give a short introduction to AGN, but I want to do it in one dimension. And the reason is AGN, the physics in AGN, they are affected also by the distance from the black hole and also from the inclination compared to some plane. But our data in AGN is mainly one-dimensional. Okay, most of the AGN are not resolved, so what we have is spectra, which is one-dimensional. And I think the more robust things we know about AGN is things that depend on the distance, and I won't get into effects that are dependent on inclination. So this is just a black hole. This is just a radius in gravitational radii, and the AGN emission spans a very large dynamical range. And this is just to get a feeling of the radii. So this is just for a 10 to the 8 black hole mass. A black hole. These are the radii. This is the Balch scale. And this is just the complementary velocity. So there's a region where the black hole dominates gravity, and then there's the region where the host dominates the gravity. And the first component in the AGN model, what we think of the AGN, is some accretion disk, some flat disk. And what I put here is just the equation for a locally emitting black body geometrically thin disk. Okay, and this is the temperature of the disk at each gravitational radii. And where we think that the accretion disk, well, at least this equation is roughly applicable, is at these temperatures. It's not very clear where this disk ends, and it's also pretty clear that something changes when we're getting very close to the black hole. And definitely this simple equation is not applicable at the lowest radii. And this disk emits photons. Okay, so what I wrote here is just the effective temperature of the photons. So if you put a black body at a certain distance, and this will be its temperature. And I put here the density of photons. And just to put all these things on the same scale, I took typical values of the coefficients here that we're seeing. And the last part of the model is just gas. Okay, this is just gas from, so there's gas on host galaxy scales, and this gas has some dependence on the gravitational, on the radius. But the question is, we don't really know how this gas changes with radii. So for simplicity, I just use this simple power law. I'm assuming that the density of the gas increases with some power law, increases as we go into smaller and smaller radii. Okay, so this gas it absorbs the AGN direct emission, it reprocesses it, and we're seeing the reprocessed emission. Okay, so this is just a very general presentation of AGN. And just from this general presentation, there's one physical point which I think is important here. So I assume here that this m, this parallel index, is smaller than 2. And if this m is smaller than 2, then what we get is that the ionization parameter, the ratio of the amount of the density of the photon to the density of the gas, it increases as you're going to smaller and smaller radii. Okay, so if the ionization increases as you're going to smaller radii, it means that the gas becomes more and more ionized as you're going to smaller radii. And when it gets more ionized, its opacity drops just because the fraction of neutral hydrogen drops. And at some point, the dust opacity, the dust which is inside the gas, the opacity of the dust is larger than the opacity of the gas. Okay, so here most of the ionizing photons will be absorbed by dust, while here most of the ionizing photons will be absorbed by the gas. Okay, and at some point when you pass, when you're very close, the dust simply sublimates simply because the temperature of the photons is too large. And again, so the dust cannot absorb the photons, and again here the gas will absorb most of the photons. Okay, so this is the basic picture, and it explains what we observe, most of the observations we've seen in the AGN in a very general way. So the disk, okay, so we have the disk component, it emits the optical, the UV, and the extreme UV emission. We have dust, so very close to the sublimation emits in the near infrared, and this is just assuming the dust is a black body, which is a very general assumption, and mid-infrared and farther, well, it's not clear that AGN emits in far infrared, but there can be far infrared emission in principle. In the gas, it emits, so it has these two zones. It has this zone which emits the lines, and this is in the host, where the host dominates the gravity. So here the lines have width, which are typical of the host. And here, there's lines which are in the black hole dominant, so they're very wide. Okay, so they're thousands of kilometers wide. And here we have this gap which does not emit the lines. Okay? So this is just the general picture. And the focus of my talk is comparing properties of the AGN on these scales with properties of the host. Okay, so this is gas on the host on these scales and on these. So that's one. Okay, so a more specific question that I want to ask. So first, there's in the observed galaxy distribution, there's a very strong bimodality. Okay, we have star-forming galaxies and we have quiescent galaxies. And I want to check which one do AGN prefer. And then I want to ask a relatively simple question, and that is, assuming that this gas that we're seeing is the source of AGN fuel, okay, the AGN fuel has to come from somewhere, then do we need quasars, which are high luminosity AGN, do they have more circumnuclear gas than low luminosity AGN? And then more general question, how do the properties of the circumnuclear gas, how do they depend on the AGN and host properties? And just to answer the question, I'll start by presenting our sample that we used. So we created a new sample, which was selected by the broad H alpha luminosity. Okay, so this is the broad line. And okay, so just one thing I didn't say before. So all this picture is an AGN that we're seeing. This is a picture for an unobscured AGN. Okay, assuming that we're seeing this region and these regions. There's also AGN where something is on the line of sight between us and the center, and then all that's to the left of here we're not seeing. Okay, we're seeing only things that are farther away. Okay, so these are, if we're seeing these are unobscured AGN, and if we're not seeing it's obscured AGN. Okay, so I'm taking a sample of unobscured AGN, so we can see the properties of the AGN, and they're low redshift. I took low redshift, so we can also see, which means that they're mainly low luminosity, so we can also see the properties of the host. And this is the sample we used. And I'll do just an analysis of what we're seeing, the observed spectral energy distribution, and then I'll answer the questions. Okay, so very quickly I'll just explain how we selected the sample. So we took the SDSS, all the optical spectrum in the SDSS, and what you see here is a host-dominated spectrum. This is the host, and we subtracted the host template, and from from the residual, you just see this broad component, which is the broad H alpha, and on top of it, you see these narrow lines. So if we found broad emission, okay, then we just entered our sample. This object entered our sample, and this is our detection limit. So sometimes the broad emission is just the small wings on these narrow lines. So these are the weakest AGN that we can see. And these are the type of AGN that we're seeing. So we have these objects which have very strong broad H alpha and weak narrow lines on top of it. And then we have these objects which the broad lines and the narrow lines are roughly comparable in flux density. And we also have these objects where the broad lines are just like a weak base below the narrow lines. Okay, so this is
How certain are you on things at the bottom are actually AGN or not just?
well, this defines our detection limit. Okay, so this is yeah.
So there was a sample of optical narrow-line AGN that Lander Kaufman and others, which you defined in the SDSS spectrum. How is your selection similar to what they did, or are the samples different?
Well, they actually use obscured AGN, so they're seeing only narrow lines. Okay, and they're not seeing broad line. And he selected against objects which use the broad line, and I'll do a comparison at a later stage. Okay. Okay, so it's just the general luminosity distribution of our samples. So
Let me just interrupt real quick. So I know it's like 100,000 Sloan to a quasar.
yeah,
And you're down to 4,000.
yeah. So two reasons. First, we're low redshift.
Oh, so you require low edge.
Yeah, we're low redshift, and second, we also have a signal to noise. We require a higher signal to noise than the minimum in the SDSS just to make the decomposition between these two components possible. Okay, so this is actually
Sorry, can I interrupt?
yeah, please.
But you have some that are very host dominated here.
Yeah.
So these were already identified as AGN candidates, or you looked at every? I mean, how did you guys do the? Did you look at
You
everything?
select out AGN or you select out
Yeah.
just spectrum?
We looked at everything. We just took all the spectra, did the subtraction. We saw here emission.
Yeah. So these are lots of things that you wouldn't get if you just did the standard AGN cuts or looked at what.
They're UPT diagrams, they don't stand out as AGN or do they? They're the standard.
I'm gonna get that.
Okay.
This concerns your question, just the luminosity distribution of the different samples. So this is the low redshift SDSS quasars, and these are objects you can be ordered down in order and a half orders of magnitude. And there's a sample here by Louis Hof, 97, which goes even much lower luminosity, but it's a much smaller sample. And this is our main difference, that at low redshift we have about 7 times the objects that in the quasar catalog. Okay, so the first question is what is observed spectral energy distribution of AGN? And I'll just quickly show what we expect to see. So if we just take this black body thin, theoretically thin disk, locally emitting, we're expecting in the Rayleigh-Jean scale of this disk, we're just expecting the spectral slope of a third, and more detailing model done by chain, so you go down to about a slope of 0. So what do we see? This is in the optical, where we're expecting this disk to be relevant. Okay, so what do we see? What we did here, we took our most luminous objects, where the host does not have a strong effect, and we binned them according to their optical slope. So these are the bluest objects, these are the reddest objects, and we added more data from different wavelengths. We added this near infrared and UV and X-ray from different wavelengths. And what you can see here, so these objects have the same luminosity of the broad H alpha. Okay. What you can see here is that the UV has a large range, so there's a big difference in the UV, but in the X-ray and in the near infrared, there's a small difference. So this is consistent with dust reddening along the line of sight. Okay, that's what's causing it. And you should notice that it's very inconsistent with an intrinsic effect. Because if we have the same broad H alpha luminosity, and you expect the UV is pretty close to 1 Rydberg. So the broad H alpha should be very sensitive to the UV luminosity, and you don't see a large difference in UV to broad H alpha between the objects. So more quantitatively, so this is just the UV to the broad H alpha compared to the optical slope, and you see this trend. And you also see that the bluest objects have roughly the expected slope we expect from the optically, from the geometrically thin disk. Okay, so it seems that what we're seeing is that we're seeing this intrinsic expected blue optical slope, and we're adding to it some amount of dust reddening along the line of sight. Okay.
Sort of maybe a 2.
Sorry?
There's maybe a 2 for big optical, or big UV 2.
So I would say this is about EBV. So these, let's say they're EBV about 0.2, so maybe 0.6.
Yeah.
It depends exactly on your.
This is quite a bit higher than what Hopkins et al. were claiming was typical AGN back in the day, right? I mean, this is more reddening.
This is more reddening. There's
So
two.
how did they screw up?
Okay, so there's two possible differences in between what we did and they did. First, they go to higher luminosity quasars. Okay, so there can be a physical difference between the luminosity we're seeing and what we're seeing. And also, they assumed some distribution in the intrinsic slope. And we did not assume intrinsic. So this causes the reddening to be a little bit lower. A little bit. Yes, a little bit lower. Yeah. Okay. So that's the possible difference, or it could be a physical. Okay. Okay, so this I just took, so this is the same plot we saw before, and I took also lower luminosity AGNs in our sample. And what you're seeing here is that as you go to low luminosity, you're seeing this increase in the near infrared, and you're also seeing this increase in the stellar absorption feature. So this is just a host coming in as you're going to lower luminosity AGN. Okay? So the SDSS aperture is about 3 arcseconds, so it can include a lot of hosts. Okay, so our first result is that the optical emission is the thin disk plus reddening plus the host contribution. Okay, so this is just a little bit technical point, so bear with me here. So what we have in each of our objects is a broad edge alpha luminosity. So we want to understand how does the AGN continuum depend on this broad edge alpha luminosity. And so even in objects which are host dominated, we can understand what we're seeing. And so what we have here is just the mean SCBs at different broad edge alpha luminosities. And you can see how here it's an AGN, it's a UV peak, AGN dominated, and here it's a host peak, sorry, a 1 micron peak, which is host dominated. As you're going down the luminosity, and these are just the SDSS quasar, the pure AGN. And okay, so here we assume the most simple thing. We assume that this mean AGN SB just simply scales linearly with the broad edge alpha luminosity, and these are the dashed lines. And you can see here that at least the UV, the expected UV, assuming this linear scaling, it fits what we're observing as a UV, at least at the high luminosity part. And this is just putting it differently. So you're seeing broad edge alpha, you see the UV luminosity, and these are the average values. And again, you're seeing that at the highest part, there seems to be a linear scaling. At the lowest part, you see the UV is stronger than the expected from the broad edge alpha. And this could be that the relation is indeed not linear. It can also be that simply the host is starting to come in also in the UV here. I'll show you evidence later that this is indeed the case. In the optical, what happens in the optical? So in the optical, we have a lot of host contribution. So to check whether this linear relation still applies, what we did, we took the implied host. Okay, we subtracted the expected AGN SCB using this linear scaling from the observed, and this is the implied host. And we simply compared this host to type 2 AGN, to obscured AGN, where we're not expecting an AGN contribution. And we just put here type 2s with the same redshifts as the different bins in the AGN. And you can see that this simple linear relation gives you the right host, assuming type 2s have the same host as type 1 AGNs. Okay? So the point here is that it seems that both the UV and the optical, okay, this is just, this is a host color. Okay, this is UV is the band of the host, and this is broad edge alpha luminosity. And it seems here that the optical and the UV scale linearly with broad edge alpha. So we'll use that result later.
So there's no ball effect.
Yeah, exactly. It seems that it's the. Okay, so there seems like there's a universal mean SCB which scales linearly with broad edge alpha. Okay, so to our questions. to the question we started, and that is, do AGN prefer star forming or quiescent galaxies? Now, I want to divide this question into two. Okay, I want to divide it to what is the mass of AGN hosts? Okay, do we see masses which are typical of star-forming galaxies or masses which are typical of quiescent galaxies? And again, what is the relation between the star formation and the AGN host? Okay, and there's a difference between these two questions that this is like the integrated relation. Okay, so we're looking on the history of the creation of the host, and we're seeing what mass do the AGN hosts have, which makes them have AGN. Okay, and this is a current relation. Now, what we're seeing now, while the AGN is on, what happens to the star formation? Okay, so this what I plotted here. This is the luminosity, the luminosity of the R band, and this is the fraction of objects of each type at each luminosity. Okay, and what you see here, so start with these two lines. So you see here that at low luminosity, the star forming, these are just galaxies from the SDSS. These two, and the classification is from Bridge-Vanada. And you're seeing that the star forming galaxies dominate the SDSS population at low luminosities, while the non-emission line galaxies are pretty rare. And as you're going to higher luminosities, star-forming galaxies become more and more rare, and non-emission galaxies start to dominate. Okay, so it's clearly bimodal difference between star-forming galaxies and non-emission line galaxies. And the difference here is just the definition here of a galaxy according to the equivalent width of the narrow lines. Okay. Now we take our objects. So this is the observed R band luminosity of our of type 1. T1 is a R sample, and this is after removing the contribution of the AGN. Okay, so this is only the type 1, the hosts of the type 1. And you see here this effect that it seems that the hosts of type 1 AGN just follow, they have the same distribution as the non-emission line galaxies, okay, with a factor of 3%. So if indeed type 1 hosts are non-emission line galaxies, and now I'm asking concerning the mass distribution, okay, so the luminosity, it follows the mass. So then a fixed fraction of non-emission line galaxies, about 3% non-emission line galaxies, simply host type 1 AGN, independent of the luminosity of non-emission line galaxies. The other option, that type 1 hosts are star-forming galaxies, would mean that 1 in 1,000 star-forming galaxies at low luminosity has an AGN, while at high luminosity, 1 in 1 star-forming galaxies has an AGN. So it seems more probable just from this plot that type 1 hosts are indeed non-emission line galaxies. Okay? And again, I'm not saying that they don't have emission lines, I'm just saying that they have the same host, the same mass distribution as non-emission line galaxies. Okay, and this is also consistent with the result of Kaufman et al., which used type 2 sample, and they showed that type 1 hosts tend to be early type. Okay, so if non-emission galaxies are also early type, with relatively large bulges, these results are consistent. Okay, that was the mass. So SDSS AGN seem to prefer non-emission line galaxies. What about the color? Okay, so the color here, so again, this is the same plot I showed you before. Just now I put here star-forming galaxies and non-emission line galaxies. And again, the x-axis for these is just I redshift match these objects to the different bins in broad H alpha luminosity. And here I show the mean host color at each luminosity. Okay, and the point here is that at low luminosity, you're seeing that the type 1 hosts have the same colors as non-emission line galaxies. And as you go into higher luminosity, it seems that the color is intermediate between non-emission line galaxies and star-forming galaxies. Okay. So the point here is that if indeed the type 1 AGN reside in non-emission line galaxies, then they have the same colors with the same amount of star formation in non-emission at low luminosity. But as you go to higher luminosity, you see the star formation is enhanced with increasing AGN luminosity. Question? So there's now if you look at this, the fact that the AGN, the star formation follows
So to do this, you have to subtract out some model for your AGN.
Yeah, so I use this linear relation between the,
So you're saying that if you do that, you get the host blue or you go higher than velocity.
exactly.
But you worry about maybe you get subtraction.
True, true. Well, the main thing I think that supports this is that if you put type 2s on this plot, they show exactly the same colors. Okay, so this is our main support. And also it's a simple relation. We didn't do something. Concerning the nature of the star formation here, so notice this is the U minus Z band color. Okay, so U band is like 3500 angstrom, which is mainly dominated by A stars, probably. This means that this star formation is on scales of hundreds or 300 million years. Okay, so we're not checking the current star formation. We're checking it on a larger time scale, and so what we're seeing here is associated star formation with increasing AGN. Okay. Okay, so these are our next results. Okay, back to our model of the AGN. I now want to focus on here on these narrow lines. So these narrow lines, they're just a measure of the host of the gas in the host on these scales, on the Balch scale. Okay. Okay. So the first question I want to ask is the relation between circumnuclear gas and the AGN, and I can't measure directly the amount of the gas at different AGN luminosities, but I can measure the covering factor. Okay, so these narrow lines are a measure of the covering factor of the gas, the solid angle that they span compared to this compared to the AGN. And if you remember, we expect to some level that quasars should have more gas. More gas means that covering factor probably is higher, and therefore we expect a higher covering factor in quasars compared to low luminosity AGN. And what we're seeing here, so this is the AGN luminosity, the broad edge alpha luminosity, and this is the ratio of the O3, which is the narrow line, the broad edge alpha luminosity. And we're seeing here the opposite. Okay, we're seeing that the O3 decreases, the relative O3 decreases as you're going to higher AGN luminosity. Okay, so it's not naively expected, but there could be other explanations for this trend. One of them is the O3. It's also sensitive to ionization and density effects in the narrow line gas. So we have to check that option. So I'll start with that. Okay, this is just another way of saying what we're saying, that the volumetric to O3 luminosity increases with AGN luminosity. So the question is this effect just in ionization or density effect in the narrow line gas? So to do that, we looked at different lines, and what you see here is just a spectrum near the H alpha. Okay, so you see here the broad H alpha, and the top are the narrow lines, and each column is a different width of the broad line, and each row is a different luminosity of the broad line. Okay, so what you can see here is that the luminous objects, the broad H alpha is very strong compared to the narrow lines, and as you're going down in luminosity, the narrow lines become more and more prominent compared to the rest of compared to the total profile. So the point is that we're seeing the same thing that we saw before. Okay, again, we're seeing this trend of decreasing narrow line compared to broad line. We're seeing this same trend in all lines. Okay, so we're seeing here, you can see here, like in the sulfur, this is the sulfur 2 line. You can see that how, as you're going up in luminosity, the sulfur 2 relatively decreases. Okay, and you can also see it here. So different widths have different sulfur 2 luminosities, but you see that at a given width, it always decreases as you're going up in luminosity. So it doesn't seem that this is some ionization or density effect. Specifically, we're seeing this at the H alpha luminosity, the H alpha, the narrow H alpha, which is not dependent on ionization and density that much. And okay, so these objects are named intermediate type AGN, and we're seeing that at low luminosity, all AGN are intermediate type. And we're seeing that the covering factor we calculated from the narrow H alpha. What this means that here it's 40%, and here it's 4%. Okay, so this is roughly the difference. It's a big difference of this covering factor. Okay, so at least to first order, it seems that contrary to what we're expecting, or naively expecting, this covering factor decreases.
Is this seen at higher luminosity?
Well, that's pretty high, 1040.
Yeah,
What's the volumetric luminosity in your top there?
So it's roughly a factor of 100.
What's that about?
100.
So it's not real high, but yeah, the answer is yeah, you see it, the higher luminosity.
Here these contour lines, we're adding it, these are quasars.
Oh, okay.
Okay, so these are all, we added, and you see this continuously.
So I just don't remember hearing this result previously.
It's called the receding torus multiplier.
But is this, no, this doesn't go with the preceding torus, so it goes the other way, doesn't it?
No, it says there's less cover factor for gas out farther out.
So the receding,
It's the same story, right?
the receding torus is explained like the near infrared emission by decreases.
Not only though, people notice it's narrow like this is
Ah, okay.
But anyway, keep going.
Yeah, okay. You're reaching the 10 to the 46 in the volumetric luminosity here, so you're reaching pretty high.
Yeah.
And I think the important part is that we're seeing that the gas at all scales, okay, from the near infrared emitting gas, mid infrared emitting gas, and the narrow lines, we're all seeing the decrease in covering factor with increasing luminosity. Okay, so this is, I think it shows some interaction between the AGN and the host gas.
I guess what you're saying is the whole free is fixed, that you're seeing more of the broad H alpha as you go to higher luminosities. That's the receiving torus.
Well, that would be inconsistent with that result because we're seeing that the broad H alpha and the UV, they scale in.
Yeah, that's why I'm confused. That we can talk about.
So it's just if it's just the black hole and you're going to, so you're seeing that the covering factor at this distance, okay, at this distance decreases, but also the covering factor at this distance decreases. So you're seeing probably this cone which is becoming smaller at all distances.
So that's why I'm saying the receding torus means the cone is becoming bigger. Right? That's why.
No.
Oh, you mean the ionization?
Yeah, I mean the cone of the gas.
Yeah.
Oh,
The cone of the gas becomes small.
Yeah. Oh.
It's fine to have some light going out, but there's nothing to catch dirt, you don't see.
Yeah, exactly. Yeah. So we're actually seeing a lack of gas. Okay. Okay, so this is just a different way of saying that on narrow lines show above them. Okay, this is just the narrow lines we measure.
But the broad lines don't. Or at least H
H alpha.
H alpha.
C4 definitely. Okay, so the narrow line covering factor decreases with AGN luminosity. Okay, this is Richard, this concerns your question. So the next thing we see, we're trying to understand the properties of this narrow line gas, and the first thing we want to know is the properties of this narrow line gas similar to type 1 and type 2 AGN? Because this is, at least the simple assumption is that what's obscuring the inner source in the type 2 AGN does not affect this narrow line gas. Okay? So these are the BPT plots. Okay? So just to who doesn't know, then it's just we're comparing narrow line ratios. Okay, so these are low ionization narrow line ratios compared to H alpha, and this is the O3 compared to H beta. And it's expected because the AGN have a harder ionizing spectrum that these hard photons they penetrate more into the gas, and they create this partially ionized zone. And this partially ionized zone creates these low ionization lines, the O1, sulfur 2, and nitrogen 2. And also you expect, simply because you have higher ionization, more harder photons, you have more of this O3, which has this ionization of about 2.5 Rydberg. So you're expecting AGN to be more on this side of these plots, and star forming galaxies to be more on this side, simply because the ionization is harder. So these plots are used to select obscured AGN samples. Okay, so these are, what you're seeing here is just the narrow line galaxies in the SDSS, and these are defined to be AGN, and these are defined to be star forming galaxies. Now, since we have another measure that we're seeing, if we know that we're seeing AGN, we can check whether this selection is indeed complete. So our objects fall here. These are just contour lines. And you can see that indeed most of our objects fall above this line. Okay, so we have about 80% fall above, and about 20% fall below this line. So, and they fall in this composite and star-forming region. Okay, so the point is that if you're using the selection, then you're missing about 20% of the AGN objects compared to our sample. Okay, but I wanted to notice something else, and that is these two regions. Okay, we're seeing here a significant region, a region with a significant number of objects, where we see type 1 AGN, but you don't see in the background any type 2 AGN. Okay, so this is something we might, well, at least if it's the same objects that we're seeing, then it should not be like this. Okay, maybe it's something, maybe it's a failure of the unified model, but we have to check our selection effects first, and I want to show you just that it is indeed a selection effect.
So hang on, you're saying
Yeah.
in this plot you're saying you don't see type 2s. So how do you
Just in this region, you don't see type 2s.
So you're saying that the gray dots there are type 2s? I mean,
Yeah, sorry. So the background is narrow-line galaxies in the SPSS.
okay.
Okay, and if they're above this line, they're defined to be type 2.
So you see in the broad line ones, you don't show this plot.
Exactly. That's the idea. And you're not expecting it first. And okay. So this is just, these are the same plots, and I simply divided now our objects according to the AGN to host luminosity ratio. Okay, so these objects are host dominated, and these objects are AGN dominated. Okay, so the background is again SPSS narrow-line galaxies as before, and the dots are our objects, and you see that at host dominated objects, the objects fall roughly where the type 2 AGN fall. But at AGN dominated objects, they start to be offset to lower and lower nitrogen 2,2H alpha and sulfur 2,2H alpha. So the offset objects are just an AGN to host, are AGN dominated objects. And so to do this, so this is, I guess it's a technical point, okay, that the SPSS has two surveys. It has a galaxy survey, okay, which selects objects which are extended. They have an extended morphology. And it also has a quasar survey, which selects also point sources. Okay, so type 2s are selected from the galaxy survey, and therefore they are all extended. But our objects are selected both from the galaxy survey and the quasar survey. So I plotted here host mass versus AGN to host luminosity ratio. And you see the distribution of the type 1s which are extended and the type 2s is the same in this plane. Okay? But the type 1s which are point sources are offset to higher AGN to host luminosity ratio. Okay? So and these are exactly the objects that we see that they are offset in the BPT diagrams. Okay? So the point is that this offset, this difference between type 1 and type 2 AGN is just it's just because that the type 2 AGN are selected to have low AGN to host luminosity ratio. Okay? So it's not a problem in the unified model. But the remaining question is, why do objects with high AGN to host have lower nitrogen 2,2H alpha and sulfur 2,2H alpha? What's the physical reason behind this? Okay, so the point here is just that there's no physical difference between type 1 and type 2s. It's related to our selection criteria. Selection. Okay, so type 1s are offset from type 2s in the BPT ratios, and it's related to the selection. The reason that type 1s are selected to the higher AGN to host and luminosity ratio. Okay, so now what is the? Now we're trying to understand what is the physical reason behind this trend. So what I did here, I took the host. This is the host mass, and this is just the nitrogen 2,2H alpha and sulfur 2,2H alpha, and this is the nitrogen 2,2 sulfur 2. And what I apply here is each line is a different luminosity. Okay, so the yellow line is a high AGN luminosity, the black line is a low AGN luminosity, and each bin here is just the average ratio for AGN with the same host mass and the same luminosity. Okay, so it's about 100 objects here in each bin. What we have here. And okay, so what trends do we see here? Okay, so the first trend we see that this nitrogen 22H alpha, it increases with the host mass, but it decreases with AGN luminosity. Okay, so this is the nitrogen 22H alpha. And the sulfur 22H alpha, there's a weaker increase with host mass, but there's also this decrease with AGN luminosity. And this nitrogen 2 sulfur 2, there's an increase with host mass, but there's almost no trend with AGN luminosity. Okay. So what can we understand from this? So nitrogen is a very strong metallicity indicator. Okay? It's a secondary product of nuclear synthesis. Therefore, it increases with metallicity both in absolute abundance and also in its abundance compared to other metals like sulfur. So it seems that the trend we're seeing with host mass is simply a metallicity trend. Okay, we're seeing the metallicity in this nearline gas increases with host mass. And this is just the mass metallicity relation which you're also seeing in quiescent gases. We're seeing the similar relation. But the trend with luminosity, it does not seem like a metallicity. Okay, because you're not seeing a significant change with nitrogen 2 compared to sulfur. So it's probably something else. Questions about this? Okay, so another, just to be sure that what we're seeing here is just a mass metallicity relation of the nearline gas. What did I do? Okay, so we searched for more evidence that indeed what we're seeing is a metallicity relation. We took here the mean spectrum of nitrogen 22H alpha of objects with high nitrogen 22H alpha and compared it to objects with low nitrogen 22H alpha. And we matched these objects in luminosity so we can get rid of the luminosity trend. And we also matched them in Eddington ratio. And I'll tell you why in a minute. And in the black line is simply the difference between these two objects. And one thing you can see that this has a roughly red slope. So if you look closely in, you can also, well, it's hard to see in this plot, but you can also see stronger stellar absorption features in this. So this is just to show that the red objects have a higher host mass than the blue objects. But I wanted to zoom in on this region, and what we see here is the broad iron 2 lines, okay? Which these are lines from the accreting gas, from the gas which is very close to the black hole, and these iron 2 lines are also sensitive to the metallicity of the gas, and you can see that they indeed increase with increasing nitrogen 22H alpha, or at least higher nitrogen 22H alpha objects have a higher iron 2, and so this is another indication that what we're seeing here is indeed a trend in metallicity. And this relation, one thing is that these iron 2 objects are very sensitive to Eddington ratio. So this is like a trend from Lawson and Green. So that's why I matched these objects in Eddington ratio. Okay, so it does seem from 4 different indicators, okay, that what we're seeing with increasing host mass, we see more metallicity in this narrow line gas. Okay. Okay, so it seems that the metallicity of the NLR and of the narrow line region and the metallicity of the broad line region, they both increase with host mass. Okay.
The broad line region statement is just coming from the iron. You don't have any other, like there's no UV lines to show, or you haven't shown it.
Yeah, okay, so we don't have the UV lines and we don't have specular and UV. What's relatively known in the broad lines is with luminosity of the AGN, there's an increase in metallicity. You see this from nitrogen 5 lines. But what we think is they're using quasar samples in these. And in these quasar samples, the host mass and the AGN luminosity are very correlated. So this is, I think, Feldman and Hamann result. Yeah. So that's also what they say, that it's not a direct relation between metallicity and luminosity, it's an indirect relation through the relation between luminosity and the host mass. And I think we're showing this directly. That relation between the metallicity of the broad magnetic region is with the host mass and not with the AGN luminosity. Okay. Okay, so this is the plot I showed you before. So this is just a question we wanted to check is where is this optically thin dust? Okay, this is the first result I showed you. If you remember that we were seeing optically thin dust along the line of sight to our AGN, and it's an interesting question where is this located? So to do that, we took these are the BPT ratios. Okay, so these are the ratios of the narrow line region. And we plotted the mean position of the BPT ratio for different UV to broad H alpha. Okay, so we saw before that UV to broad H alpha is a measure of the amount of optically thin dust, and we plotted the average position of the BPT for different UV to broad H alpha, and you can see that for a factor, let's say of 10 between 4 and 40 of UV to broad H alpha, there's no difference in the mean BPT position. Again, there's a small difference at higher UV to broad H alpha. So it seems that this narrow line region don't know about this optically thin dust. Okay, or at least the ratios don't show it. And there's a point that these BPT ratios are independent of rending outside the region. Okay, because these are lines with similar wavelengths. Okay, but if the rending was within the NLR, then the ionizing spectrum that the AGN that the narrow line is seeing should be much harder, and this harder should make a change the position of BPT, and we're not seeing this. So I think what we're seeing here is evidence that the optically thin dust is on large scale compared to the NLR, which means because the NLR is already tens to hundreds of parsecs, it means that this thin dust is on host scales. Okay, and this is just one thing I owed you is indeed this high UV to broad H alpha at low luminosity. Does it indeed look like host contamination or host contribution to the UV? And so we did the same thing, just these. So here we're using only low luminosity AGN, and before I showed only high luminosity AGN. This is the low luminosity AGN, and you're seeing that when the UV to broad H alpha becomes very high, okay, you're moving towards this composite region in the BPT diagrams, which suggests maybe that we're seeing just contribution to the narrow lines and to the UV from star formation in the host. Okay, so just another way, you're seeing, so before we saw that the maximum ratio of UV to broad H alpha is about 80, and here we're seeing it's about 200. Okay, so this is simply, we're seeing here ratios of UV to broad H alpha that we're not seeing at high AGN luminosity. This is also consistent with host contamination of the UV. Okay, so these are just to summarize my results. And it seems that the SED is thin disk, plus rending plus host, and that this rending dust resides on host scales. And it seems that the SED scales linearly with broad H alpha, and the hosts simply appear to be reside in non-emission lag galaxies, and star formation is enhanced with increasing AGN luminosity. And concerning the gas, we saw that the narrow line covering factor decreases with the AGN luminosity, and we saw that the BPT selection misses 20% of the AGN. And these AGNs, we saw that they probably have a large star forming contribution compared to the AGN. And the type 1s are offset from type 2s in BPT ratios, and it's a selection effect because they have a higher AGN input luminosity. And the NLR and BLR metallicity increases with the host.
All right, so do we have any questions?
So, when you said that AV was sort of 0.6 or whatever, or these are broad line. So, on the other hand, they're pretty close by someone, and there must be slow imaging. Can you see the host effect? Anything where you're trying to do that?
Yeah, we haven't. Oh, here's these are very luminous AGN. What we saw clearly
So the reason I'm asking is that if you look at nearby famous ones, 5548 or 631, whatever. No, the big one.
Oh, you see my.
Yeah, so there you actually see that there's spiral galaxies, those galaxies are spirals, and you see dusting. So 63015, it's obvious it's this big dusting right across the right? And if you look at
Is that unobscured again, or do you see this?
It does have broad lines.
It has broad lines. Okay, so the same.
It's a sort of 1.8 or 5 right there.
Here.
Yeah, but it's also got big X-ray columns. But actually, a lot of the X-ray absorption may be just due to the dust. You see the dust. Anyway, so I was just wondering. So in that case, if you see a meson spirals when you got holes, then you can understand why you see the genes going in the same direction as the holes. And you can imagine that there's not a lot of gravity. At least it's substantial. I'm just wondering, where is the dust getting out of the disk, or are these things spirals, and the dust getting out of the disk, or what?
Well,
Even if there's this much dust, they're not elliptical. Probably. Ellipticals don't have that much dust.
True. But we are seeing that they follow like the non-emission line galaxies in AGN, at least the luminosity
So they're
distribution.
not actually star form, or particularly star form.
Yeah. Well, they seem more star forming than typical non-emission line galaxies.
Okay, fair enough.
Yeah. But they're not star forming
They're not
galaxies.
star bursts.
I'll say in the X-ray selection from like the bat sample, so they're finding spirals mostly, but they're finding very large bulge spirals. So there seems to be a tendency here of a large. Well, it's probably because you have to have a large bulge if you want a large black hole mass. It just so the AGN will be.
It's not obviously
Well, it's not-
it has to be true.
It has to be true. Yeah. Okay. Okay. So it's more likely that you need a large bulge. And I think this is also the reason we're seeing the non-emission line galaxies have similar luminosity distribution as AGN, because our AGN there's a minimum black mass just to so we can eject it. Yes, ejected, and that may imply a large bulge. Yeah. So I think definitely this is dust, which is far away, and I would doubt if you're seeing something really edge on in a spiral, then it'll be a type 2. Okay, it's just you'll have enough column. But I haven't looked at the host yet. I think maybe more interesting result is that we're not seeing dust on very close to the AGN. Maybe, let's say that's less expected. We're not seeing dust, thin dust.
Do you know much about the X-ray absorption columns in these It doesn't look like there's much. Exactly.
It doesn't
There's
look
no
like
scatter either.
Yeah. There's one point here, one subtle point here that we fix the broad edge alpha to be the same luminosity. So if there's a difference in the broad edge alpha luminosity, we like fix it for it. We just simply fix our assumption.
But Joe, we do see systems where you have a lot of X-ray absorption and no dust absorption. So VAO makes it strong. I'm not saying no.
Yeah, right.
Where you have X-ray columns supposedly 10 to 23, and if it was absorption out of the galaxy, you wouldn't see anything at all. So and I think the same thing's true of these lower luminosity guys, where there is some X-ray obscuring gas, which is more or less dust free, but you're not seeing any X-ray obscuring gas to speak of.
So those, I would guess those would be like the broad line region clouds or something, which are dust free.
Yeah, exactly.
But there's also obscuration on
No,
lines.
exactly.
Yeah.
Any more questions? Well, let's thank Jonathan again. Jonathan's going to be here for the rest of the afternoon if you want to